By now, you're probably starting to see how chemistry can change your view of the world. Chemistry explains everything you can see, how it looks, the way it feels, why it behaves the way it does, by describing everything that you can't see. It helps us understand the biggest stuff in the universe by helping us understand the tiniest. And that's why chemistry can be kind of hard to understand sometimes. Because we are, on a chemical scale, huge. Chemistry traffics in infinitesimal particles, but we are made of quadrillions of those things. They are the building blocks of mass. We are literally massive. So mass is how we massive beings tend to understand the world. In our day-to-day dealings with substances, we need to have some sense of how much of it there is before we can use it or predict how it's going to act. For example, chemistry will be happy to tell me that the atomic structure of the sugar in this packet is 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms in every molecule, but I don't have any idea how many molecules of sugar I want to put in my tea, or how that one molecule will react with other chemicals in my body. To understand that kind of stuff, I need to know the mass of the sugar that I'm dealing with. In other words, I need to measure it. And that is why there's stoichiometry, the science of measuring chemicals that go into and come out of any given reaction. In Greek, it literally means measuring elements, and in essence, it allows us to count up atoms and molecules by weighing them. Stoichiometry, yes, contains a fair bit of math, but it's one of the most important decoders that we have as chemists. It's what we use to translate from the very small to the very big, to parlay the stuff that we can't see into the stuff that we can. And because of that, chemists use it all the time, including, yes, for sweetening your tea. Ow, hot. It's quite hot. Now, if you've been with me for a couple of weeks, and I do hope you have, you're probably thinking to yourself, wait, no, don't we already have a way of measuring elements? And you're right, we do. The real coin of the realm when it comes to measuring stuff in chemistry is relative atomic mass, the average atomic mass of all of the naturally occurring isotopes of a given element. So, for example, all of the natural carbon on Earth occurs as one of three and only three isotopes, C12, C13, and C14. They all have 6 protons, but the number of neutrons vary. And these isotopes show up on our planet in totally different proportions. So the relative atomic mass of carbon is a weighted average of these three masses, which comes out to 12.01. But 12.01 what? Well, remember when we were talking about units of measurement, we're talking about arbitrary talk. Most units, except for the ones that we use to measure time, aren't based on any real objective value. We just pick a unit, like the kilogram, and we agree for a standard on what a kilogram is, and then we run with it. The same goes for atomic mass. We measure atomic mass in atomic mass units. We made them up, and the value for a single AMU is, bear with me now, 1/12 of the mass of an atom of carbon-12. Why? Funny story. Until the mid-1800s, chemists in different parts of the world used different yardsticks for measuring elements. One of the most intuitive, and therefore most common, was to use the smallest, simplest element, hydrogen, as a baseline. But in the 1850s, some chemists, led by German Wilhelm Ostwald, proposed using oxygen instead. They preferred oxygen mainly because it combined readily with so many other elements, so they figured it would be easier to determine the weights of lots of compounds. So a bunch of guys stroked their beards, agonized over this for years, until in 1903 they decided that atomic weight, as it was called, should be measured in 1/16 of an oxygen atom. Until, in 1912, isotopes were discovered and chemists realized that you can't talk about an element like it's all the same thing. It turned out there was an oxygen 16, and an oxygen 17, and an oxygen 18, and suddenly everyone was walking around like, I don't know how much this stuff weighs anymore. This was so crazily disruptive that it took another 50 years of strokey beard meetings for everyone to decide to use another standard, carbon-12. Like oxygen, carbon is common and kind of promiscuous when it comes to what it bonds with, and since it has 12 protons and neutrons, the mass of other similar elements could easily be expressed as some fraction of it. So since 1961, science has pegged one AMU as 1/12 of an atom of carbon-12, which means that carbon has a relative atomic mass of 12.01 AMU, oxygen 16 AMU, and hydrogen 1.008 AMU. So that's how we weigh atoms. But none of this solves my tea sweetening problem. Like, I don't know how many AMUs of these molecules together are gonna make this taste good to me, or how many molecules of sugar I can consume while maintaining my slim yet robust physique. This doesn't happen by itself, you know. In order to make these calculations and predict reactions, I first need to be able to convert the atomic mass of this sugar into a standard amount of substance. Not weight, not volume, just purely objective amount of stuff. You heard me. Stuff. That, my friends, is what moles are for. Not those moles. Those are nice-looking moles. A mole is arguably the most important unit in all of chemistry because it allows us to express a chemical's atomic mass in terms of grams. And to define what a mole is, no matter what it's a mole of, we use our old standby carbon-12. There are 6.022 times 10 to the 23rd atoms in 12 grams of carbon-12, and by definition, that number of anything is a mole of that thing. That's a lot, and it is known as Avogadro's number, one of the most important constants in chemistry, and although Avogadro isn't the one who arrived at this number, it's named in his honor because he used this basic principle of comparing amounts of substances to first weigh atoms and molecules. So there are this many carbon atoms in a mole of carbon-12, and there are the same number of anything in a mole of anything else. Like a dozen roses is 12 roses, but a mole of roses is 6.022 times 10 to the 23rd roses, which would be enough roses to cover the surface of the Earth quite deep. A mole of sand would be 6.022 times 10 to the 23rd grains of sand, and if they were each 1 millimeter long, a mole of them would stretch 100 quadrillion kilometers. So you get the picture? It's a big number. But in chemistry, the thing to remember is this. A mole of any element contains 6.022 times 10 to the 23rd atoms of that element no matter what. This is what lets us translate numbers of atoms into grams. It lets us weigh the elements. All right, follow me here. 1 mole of carbon-12 contains 6.022 times 10 to the 23rd atoms and weighs 12 grams, right? So 1 mole of oxygen also contains 6.022 times 10 to the 23rd atoms, but because oxygen atoms are more massive, it weighs 16 grams. And you'll recall that oxygen's relative atomic mass is 16 AMUs. The number of atoms per mole remains the same, but the mass of a mole depends on the average mass of the element. This simply means that 1 mole of any element equals its relative atomic mass in grams. So now you got it. 1 mole of hydrogen weighs 1.008 grams, a mole of iron is 55.85 grams, and a mole of natural carbon is 12.01 grams. This is known as an element's molar mass. And now that we know the molar mass of elements, we can calculate the molar mass of any compound. All we have to do is add up the molar masses of its component elements. So for instance, the formula for this sugar, or sucrose, is C12H22O11. 1 mole of sucrose, by definition, contains 6.022 times 10 to the 23rd molecules, and since each molecule contains 12 carbon atoms and 22 hydrogen atoms and 11 oxygen atoms, then 1 mole of sucrose contains 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. Multiply the number of moles of each element by its molar mass and add them up. That's the molar mass of the whole compound. See, the mole is like our chemical Rosetta Stone. With it, we can translate anything from the level of atoms and molecules to the level of grams and kilograms. And we can use it to describe not only elements and compounds, but reactions. And you don't need a lab full of samples to do it, just a pencil and a calculator.